Hello guys, welcome on Tesla Adventures. In this video, we are going to discuss the parallel LR circuit. And as we have already discussed in the previous circuits, that in parallel circuit, we first of all cannot write this I is equal to IL plus IR. This is wrong. We cannot sum these two currents like this, and we cannot equate them with the net current because IL and IR are not in phase. They are having some phase difference. Therefore, we should add them according to the phasor diagram. And to add them according to that, we need to draw the phasor diagram. So let us draw the phasor diagram first of all. And we always know that we always draw the phasor diagram at t is equal to 0. Although we can draw the phasor diagrams at any time t, but drawing the phasor diagram at any time t would make the calculation a bit difficult. Okay, so this is the phasor diagram at t is equal to 0. So first of all, we know that in parallel circuit, voltage is same. So the voltage across resistance and the voltage across inductor is same, and it is equal to this net voltage. And hence we consider the voltage as a reference and we place it on x-axis. Now we know that the resistance has a current which is in the same phase of the voltage. So the current of resistance IR will be in the same phase with the voltage, and the inductor has a phase difference of pi by 2 between current and voltage, keeping in mind that the voltage across the inductor is ahead in phase as compared to the current across the inductor. Therefore, we can say that current across the inductor will be behind the voltage across it by a phase of pi by 2. So, we will draw the inductor current IL at a phase of pi by 2 below the voltage. Okay, and we can say that the net current will be represented like this one will represent the net current. This is the phase of net current with voltage or with x-axis, and we can say that this tan phi will be equal to IL by IR, and tan phi will be equal to V upon XL and V upon R. So tan phi will be equal to R upon XL. This is the value of tan phi, and the current I will be the sum of these two current, but we will be performing the sum by using vector laws and treating the phase as angle. So according to the vector law, if there are two vectors which are mutually perpendicular, the resultant will be under root of a square plus b square. You must have heard about this. So we can say that I would be equal to under root of IL square plus IR square. Okay, and now we can write down this I as V upon Z, and we can say that IL will be V upon XL and IR will be V upon R, and cancelling this V with V, we can say that it is 1 upon Z and it is equal to under root of 1 upon XL square plus 1 upon R square, and Z will be equal to under root of we can write it down as 1 upon under root of uh, 1 upon XL square plus 1 upon R square. Hence, it can be written as XLR upon under root of XL square plus R square. This is Z. And we know that how should we use Z or how should we treat Z in writing down the currents. So current will be I is equal to I naught sine omega t plus minus phi. Now you can see that this I naught is the peak value of current, and it would be equal to V naught upon Z, where V naught is the peak value of voltage. So I will be equal to I naught, which is V naught upon Z, and this is sine omega t plus. Now we know that the voltage has a phase of omega t, and the current is behind the voltage by a phase of phi. So we can write down it as omega t minus phi, where phi is equal to tan inverse r by xl. This is phi. So this is tan inverse r upon xl. Okay, this is the current, and this is the time equation of current, which is the time dependent function. Now, if we write down the average power loss, so we know that obviously this is parallel LR circuit, and the voltage across the resistance and the voltage across inductance is equal, and both are equal to R V, the same voltage. So, and we also know that the element which does the power loss is resistance. So we can directly write down the average power loss as Vrms square by R, because we know that VR, the voltage across resistance, is equal to Vrms, which is the net RMS voltage. And obviously we are talking about the RMS voltage because we always associate power with RMS voltage only. Okay, now if we prove this thing with the formula, basic formula, which is Vrms into IRMS into cos phi. So we can say that average power will be equal to Vrms into IRMS will be Vrms upon Z, and cos phi is the power factor. Now we know that tan phi was equal to R upon XL. If I show you, then you can refer that tan phi is equal to R upon XL. So we can write down the cos phi as XL upon under root of R square plus XL square. Okay, this is cos phi. So this is XL upon under root of R square plus XL square. Okay, so average power will be equal to Vrms square upon Z. Now Z is this one, this is Z, XL into R upon under root XL square plus R square. So this is XL into R upon under root XL square plus R square into XL upon under root R square plus XL square. Cancelling this term with this term and cancelling XL with XL, the average power loss will be equal to Vrms square upon R. This is the average power loss. Okay, and we have already written the average power loss as this directly. So we should always remember that in parallel circuits, we need not to use this formula and we need not to derive the formula. We can directly say that in parallel circuits, the average power loss will be equal to VR square upon R, where VR is the voltage across resistance upon R. And this formula is applicable for all the circuits. If you are easily able to find out the value of VR separately in the question, in series or in parallel, it doesn't matters, then you can use this formula, average power is equal to the RMS voltage across resistance upon R. You can directly use this formula in any AC circuit. But in series circuits, it is difficult to find out this thing. But in parallel circuits, we know that VR is equal to the net voltage. So we can write down that average power in parallel circuit will be Vrms square upon R. Okay guys, so this was it in this video. In the next video, we'll be discussing series and parallel LR, in fact LC circuits. Thank you.